Okay, here we are, moving into video 3 of this series, in which we're just looking at some of the anti-analysis, essentially, for the Lockbit 3 or the Lockbit Black executable. Just to get us on the same page here, last video we talked about some basic analysis of those binaries that the builder created, and in this video, what we're going to focus on is essentially the unpacked version. That way we don't have to worry about having that password passed in during debugging. And we can just jump right into to the analysis now, kind of the next stages. Some of the basic analysis, we identified the lack of strings, a lack of imports. And so it's a very common pattern here as we begin to unravel malware to have to then, once you get past perhaps a layer of packing, which isn't always monolithic, right? Sometimes the packing and just how all the code is obfuscated can be very difficult to fully unravel. But in this case, there was a distinct function here. This was the first function. And even with this version that's not, that isn't actually packed, there's no logic here, as you can see. It's just called a null sub by IdaPro. We can still unpack it to help keep our bearings. And this is the entry point here. Of course, we're looking at this binary in IDA. And so now that the unpacking is complete, we can move on to this next function. And that's what we're going to try to figure out. Now, again, it kind of makes sense that as we're unraveling this, that imports and maybe any necessary strings at these early stages are going to be required. So they're going to have to be resolved. And much like unpacking and just regular, general code obfuscation, the unpacking doesn't always have to, the import resolution doesn't always have to come immediately and all inclusive, right? It might be that every API is resolved on demand as the binary executes. So we can't guarantee also that this function is responsible for that, but this is just a general pattern. And these are the kind of activities that I start to anticipate as we dig further and further into these binaries. So let's jump into this binary. As you can see, I'm going to try to keep things a little bit simple here, just in terms of saving real estate for the video. And I have just the pseudocode view open here off to the side and have that synchronized here with the disassembly listing. So I'm going to go back and forth here a little bit between the two. If we have these in sync, you can see that hopefully between the disassembly and the decompiled results, we can stay or kind of understand, from the decompiler view or the pseudocode view, the corresponding disassembled instructions. Right? And that can be really helpful to go back and forth between the two. Now, with this one, I oftentimes, or with this particular function, and if in particular I'm suspecting that there is some sort of a API resolution, I like to just take a glance at the function itself and use the pseudocode if possible, because that gives you, maybe a little bit, oftentimes a bit easier of an understanding. In this case, I can see the same function is called over and over and over again. That is sub 405DA0. In addition to that, we can just look at the first two arguments. And this is going to take us to this unknown global variable, but this is followed by a bunch of D words. And if we just simply follow one of these D words, you can see, so I just highlighted one and hit the X key for cross-references, you can see that it's actually used as the operand for a call instruction, right? So if that's one of the arguments to this function that we're investigating, sorry, that kind of jumped us around there, then it looks like, it's very likely then that function is going to resolve a bunch of function pointers for us, or API calls. Very similar, if we look at the second argument, you can see that this is an array of D words. These appear to be hashes or checksum values. And this cluster of D words ends with a hex CC, and you see that repeat over and over here as we just kind of glance and scroll through this data. So again, this would be a very common pattern in that, this first argument is going to point to an array or a region of memory where once those functions, those APIs are resolved, it's going to store those values so they can be called later. And the second argument is going to contain an array of checksums or precomputed hashes so that the functionality that we're about to explore can go through and essentially compute based off of process internals and structures that we're going to go throughout this video. We don't have to have hard-coded strings. It can actually use the DLLs that are loaded in memory, walk their export tables to find those function names, compute the hash, and then compare it to this hard-coded list of hashes here. So you could think of this, it is helping to construct an import table. And essentially, instead of having a list of imported names like virtual alloc and virtual protect and, enum date formats W and whatever, it's just using these pre-computed values. Okay, so we've got pretty good insight into this functionality already. We don't know what V1 is. We don't know what result is. But as you highlight these, and we go back up a little bit earlier in the function, you can see that, well, this is where, for example, result is being assigned a value right up here, similar to V1. V1 is assigned the result from this function call. And so we'll be able to really kind of piece together the last couple of arguments to get a better understanding of what's going on in this function before we have to drill into some of these additional functions. So let's start with this first area here. This is called a sub 405 AEC. And you'll notice that, the decompiler versus the disassembler, if you look at the disassembly, we have a 4-byte value moved into EAX, then that value in EAX is XORed with this constant 10035FFF. That's pushed onto the stack as the argument, which is why you see this value minus 133228312. Maybe we convert this to hexadecimal value. You see that pushed onto the stack, and then there's a call to this sub 405 AEC. Now this, highlighting it, you can see it's not the same as sub 405 DA0. And so as we get a little bit further into this, you're going to realize that there are actually two layers of how this ransomware is deciding to resolve APIs. And the second layer here is quite a bit, it's quite interesting. So that's probably going to be, though, in a second or third video from here. What do we know about sub 405 AEC? Well, you can see that it must return a result because EAX is being tested. And you'll notice if we highlight EAX, EAX is called a little bit later on, right? So this must be resolving an API and returning it directly as a return result in the EAX register so that it can be called later on. So as I make these discoveries, it's good to start to rename APIs, rename functions, rename local variables. I'm going to call this direct API. And what I mean by direct is it's going to take a checksum value that's XORed, right? And this is kind of another little twist on the standard approach of doing this that this malware is doing, that instead of just providing a pre-computed 4-byte value, it's actually like recomputing by adding this XOR key here. All right, so that's another layer of just making it a little bit harder for us to detect what these APIs are, because ultimately that's what we need to do. We need to figure out what these calls, right? If we go to just not this location, but these locations, and again, I'm going to pick one of these at random, right? In order to understand what this chunk of code is doing, we need to understand what this API is. We need to understand that in order to build the context and figure out where, what the malware is doing, or in the case of our ransomware, maybe we're just really interested in how it's choosing to enumerate the file system, or what crypto it's using, or whatever the case may be. But until we peel back this layer, we don't really know for sure. Okay, so now we look at that. So that resolves an API. We know that because it is returned in the EAX register and used as an operand to a call instruction. It's done twice. So we'll have two different APIs that are going to be resolved here, as well as the result of calling this first API. So we really want to figure this out. And in order to do that, we're going to navigate into this method that I just renamed, direct API resolution, and we're going to start to analyze this function. All right, so this function is going to provide us with an opportunity then, and really become the focus of the rest of this video, on just how did they go from simply providing a hash value to getting a function pointer. It's actually really cool. I've got videos that cover it in my channel. But this is just another implementation of it. And in this case, it's part of a kind of a two-stage technique. So let's take a look here. When you notice, or when you look at in the pseudocode, you'll notice that this function begins with two conditional statements, two ifs. If this dword value does not contain a value, assign it a value, and then provide that value as an argument to our direct API resolution function, returning that to that same dword. So essentially what it's doing is it's saying, okay, before we can get into the rest of the logic here, there's a couple more APIs that have to be resolved. And it's going to do that by calling itself recursively. So by renaming that before we enter it into this function, it makes that easier to recognize this. That is, that we already had some inkling as to what it was responsible for. We're not going to do much with these checksum values, right? One of the kind of next steps analysis here would be to create a method for maybe an IDA plugin or something that would actually go through and then like resolve all of these for us. Our focus is on what exactly is this doing. Okay, so if this is called, we can see that it is returning a function pointer. So we know that this is going to be some API. When this call gets made then, right, then this will, at first, the first time through, this will now be populated. So I guess actually the second time through, this will now have a value. It's in the process of resolving that. And so now we're going to hit this conditional. This won't be. So there's going to be another recursive call. And in doing so, it's going to assign this global variable a value. This means that this will get called a third time, in which case neither one of these conditionals now will be entered because they both have values set. They're both essentially waiting on recursive calls, and the rest of this logic to resolve that API will be executed. Let's start then by setting a breakpoint in our debugger and tracing through these calls just to see what these APIs are before we get too far into the rest of this functionality here. That is, once this returns a value and this returns a value, well, then it can finish executing, and we'll go back here to resolve whatever API this is. Okay, in order to do that, I'm going to set a breakpoint on this call right here. So that's going to be at this address, 405B13. So we'll just copy that, and I've already got x32 debug open. You'll need to take note of your memory map and the fact that this execution for me is at a different image base, E10000. Okay, so this is at 5B13. So we just need to add the two together. We'll set a breakpoint at E1 5B13. All right. We can go also, so we just catch the default breakpoints here. We'll catch the breakpoint at the program entry. All right, here's unpacking. Here is where we're going to step into. And then beyond this call is ransomware stuff, right? So I'm going to set a breakpoint here just in case I make a mistake. I can catch execution before we get into ransomware ops and probably stop it or restart it. All right, so now let's go ahead. We'll hit go. We hit our breakpoint. There is that first call. Right? So here's the compare. There's the jump. And now that's that first call. So we're going to step into that. Okay, now we've just recursively called ourselves. We're not going to enter that if statement. We're going to enter this one though. And I'm not going to step into this one. Instead, we're going to step over, and you'll see in EAX, we have now the address for LDR get procedure address. This comes out of NTDLL. All right, so what does that mean? That means this right here is LDR get procedure address. Okay, this makes sense. Start to think about it. If we want to resolve a bunch of imports and load a bunch of libraries, then there's typically two APIs that we need, load library and get proc address. And what this malware is doing is instead of using those from kernel 32, which is maybe more of a standard library or a standard way of doing it, it's getting equivalent functionality out of NTDLL, which is just a lower level API or low level library. Okay, we can also, going back to our debugger, right, here's that call. Well, we can set a break here. We can let this run, and now we can see inside of EAX, that was LDR load DLL. All right, so yeah, that makes sense. Let's change this global variable. See, I've already got those values there. And now that that's finished, now we can get into stepping through this logic to see how it's resolving the function pointer for this hash right here. In order to do that, we're going to first explore using the disassembly, and then we'll also annotate and update our decompiled results here as we go, although you can kind of see that IDA has already done a little bit of that with some of these structures. So to help keep these videos just a little bit more digestible, I'm going to go ahead and wrap things up for here. This was kind of like the preamble to getting into how this API resolution is done. Now we're going to get into the API resolution by specifically looking at the PEB structure, how it's going to walk the export table from the DLLs that it finds in memory, and then how it actually creates those computed checksum values. So hope you enjoyed the video so far and the series in total. I'll see you all in the next one.